If you're watching this video, you probably know about the number pi. You likely have the intuition that pi is the number of diameters it would take to cover the circumference of a circle. Pi is a fairly straightforward number to understand because it's so easy to visualize.
You've also probably heard about the number e. However, you may not be able to visualize it in the same way you can visualize pi. Unlike pi, e has a whole host of different descriptions used by different people, none of which are particularly enlightening. While these formulas may seem scary or unfamiliar, there's actually an elegant way we can tie them together and show how they all stem from the same fundamental bit of intuition.
This is Tally. She's a one-dimensional creature, not made up of cells, but rather continuous, infinitely divisible matter. She has the curious property that every arbitrarily small bit of matter in her body grows at a constant rate, in such a way that it would duplicate itself over the course of a full day. Since every piece of her body is growing at the same time, collectively, her growth looks like this. To make it easier to differentiate between her initial body mass and the mass grown over the course of the day, we'll recolor the growth due to her initial mass as orange. This animation is a simplification of what her true growth looks like for a number of reasons. For one thing, we've only subdivided her body into around 30 regions that each grow their own mass. But really, every piece of her body, no matter how small, works to duplicate itself. Also, for clarity, we'll collect all the growth at the top of the creature. You might be questioning how this has anything to do with E, but if you bear with us to investigate the effects of Tally's growth rule, you'll see how all three descriptions of E pop out. Our goal will be to find an expression for Tally's height at any point during the day.
To understand Tally's growth, let's plot her mass over time, which, for a one-dimensional creature like Tally, is just her height. Say at the beginning of the day, she's 1 meter tall. Over the course of the day, her initial red body mass will effectively duplicate itself, because every tiny piece of it duplicates. Here, the red line represents her initial body mass, and the orange represents the growth due to that initial mass over time. The white line plots her total height. So, we might expect Tally to be 2 meters tall at the end of the day, 1 meter of initial height, and 1 meter of height accumulated throughout the day. However, she will actually be taller than 2 meters, because the new orange mass will be duplicating itself throughout the day to create more mass we haven't accounted for yet. For instance, between 2 and 3 a.m., Tally will have grown for 1 hour, which is 1/24th of a day. So Tally's initial mass will have grown an additional 1/24th of a meter, or about 42 more millimeters. But this new 42 millimeters of mass is now a part of her body, so it behaves like any other part. It grows. Specifically, it also grows at a linear rate for the remainder of the day, where if it were given a full 24-hour period, it would duplicate itself. But there are only 21 hours left in the day, so this 42 millimeters of mass will only grow about 37 millimeters of new mass by the end of the day, not a full 42. The exact numbers aren't important here, but what does matter is that all of Tally's mass grows linearly, including any new mass.
So, you can see that Tally's growth is actually quite complicated. Her initial red mass contributes some amount of new orange mass, 1 meter to be specific. But this meter of orange mass accumulates some amount of new mass throughout the day, which we're coloring yellow. The total yellow mass will be less than a meter because not all of the orange mass is present at the beginning. It's only gradually accumulated. Similarly, whenever new chunks of yellow mass are created, they'll begin growing some mass of their own, which I'll color green, and so on. Even though we started with a fairly simple description of how Tally grows, under closer inspection we got a complicated process that seems infinitely layered. But I want to reinforce the intuition that at a high level, Tally's growth is very straightforward, and the color differences are purely pedagogical. There's no difference between how her initial mass grows, to how her orange mass grows, to how her yellow mass grows, and so on. All that's happening is that every arbitrarily small bit of her body grows at a linear rate so that it would duplicate itself throughout a day, and of course this means that any pieces of newly created mass will themselves start growing. In fact, it might even seem that this is the most natural way a creature could grow.
Nevertheless, it's still a daunting task to calculate her height over time. When faced with a difficult problem, one important problem-solving strategy is to not focus on the whole problem at once, but rather a simple part you can solve. Solving the simple parts may give insights on how to approach the more complicated ones. We'll also want to identify the simplest units to work with, which in our case would be days, because Tally's growth is defined in terms of a day-long time period. Hence, we've relabeled the horizontal axis from 0 to 1, representing the fraction of the day that has passed. And the time box in the upper left corner will also show that fraction.
A very simple question we can ask is, after X amount of the day has passed, how much orange mass has accumulated? In other words, how much new mass is her initial mass responsible for? You may already know the answer. Since she starts out with 0 orange mass, but has 1 meter of orange mass after 1 day that's accumulated in a linear fashion, her orange mass after X of the day has passed is simply X meters. For instance, when 60% of the day has passed, the amount of orange mass will be 0.6 meters.
Okay, simple enough. Here's the next question. After X amount of the day has passed, how much yellow mass has accumulated? Remember, the yellow mass is the mass that grows from the orange mass. Calculating this will be slightly more difficult, because not all orange mass is created equal. Orange mass that grows near the beginning of the day will contribute much more yellow mass than the orange mass that grows just before time X, because that new mass won't be growing for nearly as long. We can tackle this problem by breaking up the day until time X into small chunks of time, delta t, and calculate approximately the yellow mass generated during each small time chunk. Then, we'll sum everything up to get an approximation for the total amount of yellow mass generated up until time X. To turn our approximation into an exact value, we'll see what happens as the time chunk delta t gets smaller and smaller.
At time t, the amount of orange mass generated so far is orange of t, which is just t. To figure out the yellow mass generated during the period from time t to time t plus delta t, recall that the orange mass we already have is growing at a linear rate in such a way that it would double itself in a one-day period. Thus, since a delta t fraction of the day passes, the orange mass we have only produces a delta t fraction of itself as yellow mass. In other words, the amount of yellow mass generated is the amount of orange mass we already had times delta t, or t times delta t. However, this is only an approximation to the actual amount of yellow mass generated because the orange mass created between time t and time t plus delta t also generates yellow mass, which we've ignored in our calculation. We'll get back to how to fix this in just a minute.
Now, remember what we're trying to do. We're trying to calculate the total yellow mass created until X amount of the day has passed, and we know approximately the amount that's generated in every small time interval. So all that's left to do is sum these small amounts up to get the total. However, there's a much simpler way to view the whole procedure if we take a closer look at the quantity t times delta t, which, as we saw before, is approximately the amount of yellow mass generated between time t and time t plus delta t. The key observation is that t times delta t is also the area of this rectangle, because it has height t and width delta t. Hence, summing up the amount of yellow mass generated in each small time interval is equivalent to summing up the areas of all the rectangles. Therefore, the sum of the rectangle areas is approximately the total yellow mass. But also, notice that the sum of these areas is about the area under the orange graph. So it's plausible that the exact amount of yellow mass is the same as the exact area under the orange graph, since the sum of the rectangle areas approximates both of them. To prove it, we'll investigate what happens as we make delta t smaller and smaller. As delta t decreases, the sum of the rectangle areas gets closer and closer to the true amount of yellow mass accumulated, because there's less time for unaccounted orange mass growth. But the sum of the rectangle areas also gets closer and closer to the area under the orange graph. Thus, since the amount of yellow mass accumulated and the area under the orange graph are both the limit of the same process, they are equal. The total amount of yellow mass accumulated is exactly equal to the area under the orange line. If that explanation wasn't completely satisfactory, you should pause and think more about why the sum of rectangle areas gets closer and closer to the true amount of yellow mass generated. We've left some text on screen to guide your thinking.
Using some basic geometry, we can calculate the area under the orange line. This is simply the area of a right triangle with base length x and height x, which is 1/2 x squared. Alternatively, for those of you that know calculus, we could have computed the area with an integral. The integral from 0 to x of t dt is 1/2 x squared. So, the function yellow of x, representing the amount of yellow mass generated until time x, is yellow of x equals 1/2 x squared.
Now, we have a pretty good approximation of Tally's height at any point during the day. She has some amount of initial red mass, some amount of orange mass, orange of x, that was generated from the red mass, and some amount of yellow mass, yellow of x, that was generated from the orange mass. However, when bits of yellow mass are generated, they produce new mass, which will color green. Our next task will be calculating the total green mass produced after X amount of the day has passed.
You may see where this is going. We'll take a very similar approach to how we calculated yellow of x. Break down the day into small time intervals of length delta t. At time t, the amount of yellow mass Tally has is yellow of t, which is a half t squared. This mass will grow linearly, producing green mass, for a delta t fraction of the day until time t plus delta t. Since the growth is linear, and the yellow mass would double itself if given an entire day to grow, the amount of green mass produced is a half t squared times delta t. This is also the area of a rectangle of width delta t placed under the graph of yellow of x. Summing up the areas of all the rectangles from 0 to x gives an approximate value for the amount of green mass generated. And taking the limit as delta t goes to 0, we see that the green mass generated before time x is exactly the area under the function yellow of x. Now, if you're not familiar with calculus, you'll have to take this next bit on faith, but for those of you who are, you'll recognize this means green of x is the integral from 0 to x of yellow of t dt, which is 1/6 x cubed.
Going forward, we can extend this pattern without going through all the details. The green mass produces new mass throughout the day, which we're coloring blue. The amount of blue mass generated until time x is the area under the function green of x, which is the integral from 0 to x of green of t dt, or 1/24 times x to the fourth. And when blue mass produces purple mass, the amount of purple mass produced before time x is the integral from 0 to x of blue of t dt, or 1/120 times x to the fifth. This process continues indefinitely.
With all the work we've done combined, we can get an expression for Tally's height. After x amount of the day has passed, her height is her initial red mass, plus her orange mass, plus her yellow mass, plus her green mass, etc., which is the sum 1 plus x plus a half x squared plus a 6x cubed, and so on, where each consecutive term is the integral of the previous term. We can write this in a more compact form by realizing that the denominator of each fraction is the factorial of the corresponding exponent. For example, in the term 1/24 x to the fourth, the exponent is 4, and the denominator is 24, which is 4 factorial. This pattern emerges because of how integration works. Taking the integral of 1/24 x to the fourth increases the exponent by 1 to a 5, but then multiplies the denominator by 5, so the denominator is still the factorial of the exponent. So, Tally's height after x amount of the day has passed can be succinctly expressed using summation notation as the sum from n equals 0 to infinity of 1/n factorial times x to the n.
Awesome! We got an exact expression for Tally's height at any point during the day. But this expression isn't exactly simple. It's got infinitely many terms after all. It turns out, though, that we can look at the problem at a slightly different angle to get a completely different, arguably simpler expression for Tally's height throughout the day.
As before, let's attempt to calculate her height after a certain fraction, x, of the day has passed. This time, we'll use a procedure to estimate her height, so we won't get exactly the right answer. What I mean is this. One straightforward simplification we can make is to assume that all of Tally's growth until time x happens at time x, which simplifies things because now we don't have to worry about all the growth that happens due to mass other than her initial mass. Since her growth occurs at a linear rate in such a way that her 1 meter of initial mass would double over a full day, she would accumulate x meters of mass at time x. Based on the simplification we're making, we assume all x meters instantaneously come into existence at time x. Thus, her total height is 1 plus x meters.
Now, you might be complaining that this is actually a terrible estimate, because we've completely neglected any growth that occurs due to the x meters of height she accumulates. In other words, we're ignoring the yellow, green, blue, and so on mass she accumulates that we worked so hard to calculate before. Fair enough. What if instead of only counting her height at time x, we break her growth up into 2 periods? We let some growth occur at time x/2, and then some more occur at time x. This would improve our estimate because now we'd be accounting for some of the yellow mass that grows from the orange mass that grows during the first x/2 period. Thus, at time x/2, x/2 meters of orange height instantaneously come into existence, so her total height is now 1 plus x/2 meters. Then, during the next x/2 time period, both the red mass and orange mass grow by another x/2 fraction of themselves. But really, the color distinctions don't matter here. All of Tally's mass grows in the same way. So instead of distinguishing between red and orange mass, we can think of the entire 1 plus x/2 meters of height growing by an x/2 fraction of itself, which, according to the linear growth rule, means she should gain an additional 1 plus x/2 times x/2 meters of height by time x. Thus, her height at time x is 1 plus x/2 plus 1 plus x/2 times x/2, which is just 1 plus x/2 squared.
This estimate still isn't the greatest because, for instance, there is unseen mass that grows between time 0 and time x/4, which itself grows new mass until time x/2, and our calculation doesn't account for that. So what if we instead take her growth into account at n evenly spaced intervals, where we could pick n to be some very large integer? This would greatly improve the estimate because the amount of time during which unseen mass grows is decreased. Let's see this in action. Between time 0 and time x/n, her initial 1 meter of height grows x/n meters. Thus, her height at time x/n is 1 plus x/n. Then, this mass grows for another x/n time period, so we multiply it by 1 plus x/n. The 1 keeps the mass we already have, and the x/n increases it to account for the growth. So, her total height at time 2x/n is 1 plus x/n squared. Now, this mass grows for another x/n fraction of the day, so we multiply it again by 1 plus x/n. This means her height at time 3x/n is 1 plus x/n cubed. You can see where this is going. At time kx/n, Tally's height is 1 plus x/n to the k. So, when k equals n, her height at time nx/n, or x, is just 1 plus x/n to the n.
However, even if we take n to be enormous, the value 1 plus x/n to the n is only an estimate of her height at time x, because there is still unseen mass growing between the times when we calculate her height, whose growth isn't accounted for during that period. To fix the problem, we would need to be breaking the day up into infinitely many intervals. But of course, that doesn't make too much sense. Instead, we can see what happens to the estimate as n approaches infinity. We'd expect the quantity 1 plus x/n to the n to be a better and better approximation of her true height. So her height at time x is the limit as n goes to infinity of 1 plus x/n to the n.
Not bad. We now have two expressions for Tally's height at any time x, calculated in two different ways. At first glance, these equations look quite different, and that stems from us looking at Tally's growth from different perspectives, but they do both yield the same result. For instance, if we use a calculator with x equals 1 in both formulas, we get about 2.71828 either way. And for those of you that have seen the number e before, you would recognize this constant as e itself. Indeed, this number is exactly e. In this context, e is Tally's total height at the end of one day.
But e is more than just a destination. It turns out that e can completely describe Tally's growth at any point during the day. So e is fundamentally embedded in Tally's growth rule. Amazingly, Tally's height at any point during the day is just e to the x.
To see how, first realize that if at any point during the day Tally grows for a delta t amount of time, her height gets multiplied by the same amount it would be multiplied by if she were growing starting from time 0. We won't prove this fact, but if you're curious about the details, you can try to prove it yourself using either of the two methods we've shown so far. What this means is that if Tally's height is height of t at time t, then her height at time t plus delta t will be height of t times height of delta t. We can use this fact to show that Tally's height at time x is e to the x.
Let's assume x is rational to start, which means x equals a over b for some integers a and b. We can break the interval into a time segments, each of length 1 over b. We know, by definition, that her height at time 1 over b is height of 1 over b. Then, from time 1 over b to 2 over b, she grows for a 1 over b time period, so, by what we established earlier, her height would be multiplied by height of 1 over b. Hence, her height at time 2 over b is height of 1 over b squared. This continues until time a over b, at which point Tally will have grown for a 1 over b intervals, making her height of 1 over b to the a. So all that's left is to figure out what height of 1 over b is.
We can do this by using what we already know. Let's leverage the fact that height of 1 equals e by breaking up the interval from 0 to 1 into b time segments of length 1 over b. By the same logic as before, her height at time k over b is height of 1 over b to the k, for any integer k. Thus, her height at time b over b is height of 1 over b to the b. But we know her height at time b over b is e. That tells us that height of 1 over b to the b equals e, or height of 1 over b equals e to the 1 over b. Hence, her height at time x is height of 1 over b to the a, or e to the a over b, which is just e to the x.
However, we had to assume x was rational for this argument to work out. The main reason we can't use the same logic for irrational numbers is that e to the x is defined differently when x is irrational versus when x is rational. However, it's still true that Tally's height at time x when x is irrational is e to the x. We've left some details on screen to guide your thinking if you're curious about the proof.
The main takeaway is that Tally's growth rule is fully described by e. E is not just some value that she grows to, but rather a natural base for describing her height at any time throughout the day.
Now, if you knew anything about e before this video, there's one more infamous fact you're probably wondering about. Why is e to the x its own derivative? In our framework, this is simply asking why the rate of change of Tally's height is equal to her height. The reason is actually quite straightforward. Let's try to calculate the instantaneous rate of change of Tally's height at time x. Her height at time x is e to the x, and based on how we know Tally's growth works, this e to the x bit of mass will double itself if given a full day to grow. However, if we observe its growth for a tiny fraction of a day, say for a time interval of length delta x, the e to the x mass will linearly grow by a delta x fraction of itself, which is e to the x times delta x meters of additional mass. Now, in this calculation, we haven't accounted for the growth due to the growth over the interval, or the growth due to the growth due to the growth, but that's okay. Because delta x is such a small time step, hardly any growth happens in the first place, and any growth produced by that growth will be negligible.
To find the derivative of her height function, we take the difference in height between time x and time x plus delta x, and divide by the length of time, delta x. Taking the limit of this ratio as delta x goes to 0 gives her instantaneous rate of growth at time x, which is e to the x. Thus, the derivative of her height at time x is e to the x, which is exactly the statement that the derivative of e to the x is e to the x.
At long last, we've recovered the 3 facts about e that we mentioned at the very start of the video. But recovering those facts wasn't really our main objective. We hope to provide some solid intuition for where e comes from and how it's related to continuously growing phenomena. We hope that you came away with a sense that Tally's growth is extremely natural, and e, being the constant that it is, that perfectly describes her growth, is a fundamental constant.
Of course, the math in this video was only intuition, and it isn't a substitute for a true proof, which is why we've linked several resources in the description that rigorously prove everything shown here.
Thanks for coming along on this journey with us. Have a good night. Top tier ending. We're done. No.